Okay, so in this video, I'm going to talk about world models. As background, I'll first explain how modern image models are being trained, including an idea called neural assets. From there, we'll move on to a whole bunch of other interesting stuff, and we'll finish up with a free Colab, which you can run yourself to see world models run in a tiny sense for free. Okay, so this is an overview slide. Image models are getting very good these days. Clearly, huge data helps, but there are a lot of tricks which are not really very disclosed. So I'm going to go into some of these and maybe some speculation about how these things are now being trained. I'm not going to touch on video models except to talk about world models. These things are now taking off, and these may be a setting in which robots can be trained in silico, meaning they can be trained offline without having to interact with the real world, which can be very expensive. As I mentioned before, I've made a free Colab, which is linked in the description, which will allow you to see these world models for yourself for nothing. So first up, I've got 3 topics here for image models, and then we can move on to world models. So a key issue facing image models are they faithful to the captions we're providing? Now, one of the key things that image models rely on is that the captions people are providing on the internet are actually good. We'll see how image models are now getting around problems with that by a process of both filtering out bad captions and also improving the captions that do exist. Okay, so this is taken from the Qwen-Image technical report, where they show in various stages how their initial huge pool of images were filtered down in different ways to provide different quality of images at different parts of the pipeline. Some of the filtering includes such stages as comparing the caption clip embedding to the images clip embedding. Clearly, if these are too dissimilar, then the clip model disagrees that they relate to the same image. And that could be a sign that the captions are a bad place to start training an image model from. So this diagram just provides an idea of the kind of detailed work that is required in cleaning an image dataset for training one of these models. Now, moving back to the launch of DALL-E 3, OpenAI released a technical report where they explained some aspects of how the model was trained, obviously leaving out huge numbers of details. But one important nugget was how they were fixing up captions to make them more descriptive. And we can see this has also been adopted by Stable Diffusion 3, and that they use explicitly a captioning model, this CogVLM, to provide essentially the same function. So here's an illustrative example from the DALL-E 3 technical report. If we look on the left-hand side, we can see it's clearly a bathtub, a fancy bathtub in a modern setting. But the original caption provided in the alt text online was now at victorianplumbing.co.uk. Now, what we would have seen with the original Stable Diffusion kind of models is that would have been taken as being the caption, and all of the images could be aligned to that. So that if you came up with a caption which was Victorian plumbing, you could get this image. Clearly, this shows the amount of noise that are in these captions, and the idea here is to fix these up. So the second line down here is what a simple captioning model would say. And then the third example is what a full-blown captioning model would say. And so here, instead of going for just a description of kind of the main thing in the image, this is a super detailed description of every aspect of the image. Now, the benefit of doing this is if your caption thoroughly matches your image, then the model learns to thoroughly match captions with images. I.e., if you give it a detailed caption, then it knows all the aspects of the image it should produce. If it had only been trained with the initial poor captions, clearly given enough images, the average caption for this bath scene would have been about right. On the other hand, you're essentially telling the model to make up lots of details. Whereas with the full caption, you're telling it all the details that do appear in the image and how these will be reflected in captions. So these detailed descriptions not only give the model certainty in how detailed descriptions should be rendered on screen, but also make the dataset more useful overall. Now, this element of extra descriptive data about the image being introduced is something which we come back to repeatedly during this video. Something else which has happened with these models recently is the ability to alter images or incorporate elements into a single output image. Now, I'm not going to go into this in detail here, but the basic approach is to treat this more like a language modeling task where images are treated as tokens and can be reasoned about. This is in contrast to the old stable diffusion methods, where you might have the diffusion model relying on embeddings to influence it at each step, or a side-by-side LoRa which could be controlling it. Those methods are very customized, whereas a token-centric approach can learn about a much more general editing case. So again, here's an image from the Qwen-Image architecture. Really, I'm just showing here that they're using the pre-trained Qwen 2.5 VL model and also VAE encoder. Both of these are pre-trained, and they're using these to supply tokens into a token process. And so here is an example of the different kind of tokens that can be put into this backbone. Here we've got both system prompt, input images, user prompts. We've also got example input and output images, all of which can be trained on this one backbone. And where do we get these examples from? This is also from the Qwen-Image paper, where they talk about generating synthetic data from combinations of prompts and images in order to get trainable pairs out. These synthetic pipelines play an important role in getting the different kinds of user interactions trained into the model. Now, as the third part of the modern image training piece, I'd like to talk about neural assets. This is a paper from mid-2024, and it has a nice project page, and we'll have a look at that. So here's the project page for this. Interesting to see the number of times Google entities are appearing here. Let's scroll down to the key idea. So the pipeline here involves taking frames from videos and identifying regions of interest, and then turning those regions of interest into representations. These will be the neural assets. If you do this for 2 frames in the video, then you know that the representation for an object changes between those frames. But you can also explain how that change occurs. You would also know how the representation gets updated. So this would allow you to essentially create a caption of how the representation is moving through time. Now, this is a very interesting idea because we're looking again at how adding additional information which can be produced automatically to annotate how things are changing will then allow you to generate changes yourself. So the training task becomes, suppose I have these neural representations and I give you this change you need to make. What would the neural representations be? And if you were to reconstruct the frame using the new representations of the image, would you get the other frame from the video? So video data can give the model an idea of objectness as it relates to these neural assets and how they can be manipulated. And in particular, it will be able to manipulate these independently of the rest of the frame. So here's some concrete examples using a Waymo open dataset. On the left, we start with a source image, and then we essentially use the neural assets unmodified to try and reconstruct it. But then we can say, okay, let's translate one of those assets, and we can actually make the cars move forwards, or we can rotate them in place. So how do we get these rotating in place? Well, it's because we've also had video frames where we see cars from different angles as time progresses, and we then work out the orientations between those things and apply that orientation change to the neural assets. So this will then allow us to spin cars in place or rescale them, as in the last column. And here are further results which also show that we can now move cars around at will and rotate them, even though those scenes are outside of our actual training data. Doing this with cars is just one example. Clearly, we can do this with a lot more objects. Here we've got office scenes, we've also got camera movements, and hopefully you can begin to see that this is a quite general technique which can be applied to reasoning about objects in images. Finally, we can think about completely different operations that can be applied to these neural assets, including deleting objects, replacing them, recomposing the scene. All this leads to quite a general technique for manipulating objects within images. So to recap, what we have here is a way of training image models from videos, where we've used the representations we can pick up using other models to essentially provide captions about how to manipulate tokens within a language stream. In summary, this could allow the new image model to understand objects within the image and manipulate them at will. So with that background, let's now talk about world models. So from a reinforcement learning point of view, the idea of world models have been around for a long time. But when it comes to language models, the question is, do they really understand how the world works? Or are they simply really good at giving you text, which gives you an impression that they understand how the world works? It's difficult to actually probe them about what they truly believe about the world. So the question arises, what would actually persuade us that they do truly understand what's going on? Ideally, we'd have a model which we can actually interact with. So as a warm-up, let's talk about Minecraft, where the world model is an actual piece of Java code which runs. I originally came into contact with this from a machine learning point of view when OpenAI released a foundation model for Minecraft as part of the Basalt competition for NeurIPS. For that, I put together a bunch of Colab notebooks which explained how to get the MineRL environment working for free. So over time, I've kept tabs on how these Minecraft players are working. One notable example would be this Voyager work from NVIDIA, which is very impressive, except that it uses a Minecraft-aware tool called by a large language model. So it doesn't really have a model of the world itself. It has read all the Minecraft blogs, and it also calls a tool which is very aware of how the Minecraft world works in code. So this is actually making use of a world model, but the world model is the actual world itself. So in some sense, this doesn't count. But now let's look at OpenAI's VPT model from the perspective of annotating images or annotating gameplay. What OpenAI did is they employed people to play Minecraft according to some instructions, but also recorded what they saw and the keys that they pressed at the time. Now this resulted in low thousands of hours of gameplay, but excellent frame-wise annotations. But by training a model to predict the annotations, OpenAI was then able to label up huge numbers of YouTuber videos with accurate actions so that you could then learn by example from this huge dataset of videos which not only had the actions and the screenplay, but also had transcripts of what the YouTubers were trying to do at the time. Thus, OpenAI was able to leverage up a small number of paid-for interactions into a very, very large dataset of annotated examples, along with strategies and tips and tricks coming from YouTubers, all sourced from the internet. So now let's move on to a much more recent work called Dreamer v4 from Google DeepMind. The idea here is that they would train a model that would predict what the Minecraft server frames would look like given user interactions. And having trained this model purely by observation, they could then get another model to learn purely in simulation. Now, it may seem strange that you want to learn in simulation when the actual game of Minecraft is a simulation, but they also applied this to real-world robot videos and learned to predict what the robot would look like in simulation, and then trained a robot controller in simulation. So this is directly applicable even though the original setting is Minecraft to Minecraft. So in this Minecraft setting, they managed to play Minecraft using only this offline data. So only by observing what a Minecraft server would say, you could then train your player in this simulation of that, with the net result that this could outperform OpenAI's agent with 100 times less data. Moreover, it could get to obtaining diamonds, which is about 20,000 sequential actions, purely based on its training in simulation. I'll put a link to their project page in the description, and here are some images of their imagination training, where these are simulated images instead of real-world Minecraft images, and you can see that the simulation is pretty faithful, which would of course mean that the agent has a good chance of learning useful information in simulation. And also on their project page, we can see how they applied this to real-world videos for training robots picking up various objects. Okay, and so now we're getting on to some of the hottest news of the day. Here we have the State of AI report, which just came out a couple of weeks ago, where they traced through from the original GENIE, which is February 2024, through to GENIE 2, now GENIE 3, which is an absolutely remarkable achievement. So DeepMind's GENIE 3 is a real-time interactive video game, essentially, where you can give it a prompt to create the world and then just walk through the world and act in the world. And so here we can begin to experiment with how much the model actually knows about the world, and it's relatively convincing. One of the examples I like from their demo reel is how you can paint on objects within the world and then move around or even look away from those objects, as is happening here, and that when you look back, your changes to the world are maintained consistently. Here is another thing: they can actually in real time prompt with text things which should happen in the world. Or, here's a man in a chicken suit, here's something going by, here's a dragon. These are extremely impressive, and it's difficult to argue that these models don't have a world model internally. Now, even outside the proprietary labs, we also see the beginnings of these real-world datasets with huge numbers of hours of video, all annotated with objects and descriptions and captions. All of this is the kind of data that you'd need to actually build an internal representation of how the world works in one of these models. But rather than train our own GENIE 3, I thought the interesting thing to do is look at TinyWorlds. This is an open source world model inspired by the GENIE series. So while the headline here is rather ambitious, the reality is that these are like 3 million parameter models which are trained on datasets of videos. So each of these models is trained on a rather small image of gameplay for each of these 6 games. So the author of TinyWorlds put together a nice demo reel in addition to explaining exactly how the models work, plans for the future, and releasing the code and pre-trained models. This is a really nice release, and I thought I could add to it by creating a Colab demo whereby people could load up the models and play with them in real time for free. So the basic architecture of this is we put in contextual frames at the bottom here, which are converted into tokens, which are then modified to predict the upcoming frames. But the modification also takes place with the actions which are being performed. So as an example of the tokenization, here's what is happening with the actions. For every step in the video, a representation is found for the thing that would have made the scene change from what it was to what it should be. And these representations were then quantized so that there would only be a specific number of actions which were allowable, which would then allow us to talk about concrete actions as tokens. So here, as promised, there's a demo, and there's a link in the description below for the free Colab notebook, which will fire up one of Google's free GPUs so you can play with this yourself. Okay, so I won't go through this in too much detail. You can look at the Colab for yourself. But basically, what it does is it pulls in the TinyWorlds Git repo. It then loads up a dataset, and here you can define which of the 6 datasets you want to pull in. And I found some ideas of what good settings are. You can then pull in models for those which have been pre-trained using a few hours or few days of H200 compute by the author of the repo. It then pulls in some config settings. It then loads up the models. So in order to make the Colab work in real time, I had to essentially unwrap some of the functionality the author had built into the repo. First off, I have a reset game function. And then I have a real-time update game state function, which will get called repeatedly from JavaScript. So I've built a process here where Colab is producing JavaScript, which is repeatedly calling back to itself to update the game state in real time. And so the final JavaScript cell here basically is a loop around looking for what actions are pressed, calling back to a kernel which has been registered in Python to do the torch forward pass to produce the new image which is displayed in JavaScript. So when we play this, you will see an image, and this is pole position, where you can clearly see that there is a road here with a car going along it, plus also these 16 quantized states, which I've had a go at labeling. So what we see here is the model being updated in real time, given that it was trained at a 2 frames per second rate. And we have the 16 different actions here, which are the tokenized versions of the actions which occur between frames. Now I've had a go at annotating some of these, and in particular, I know that if I press this LB, I will get a leaderboard. So you can see here that this is what happens when you go into the leaderboard state of the game. Now it's resetting to being the car going along again, hopefully. If we press the map button, it will give us a map. So this is another state of the game which we can get for pole position. And as another example, let us press the right button, which will steer our car to the right, which will cause it to eventually crash. There we go. I think we see a fiery crash here, and you may have to use your imagination a little to see that that's what's going on. So another interesting aspect of this is if we start to press some of these buttons, the model doesn't necessarily know whether I'm causing the action to be performed or whether things are happening and the action is taking place. So for instance, if you press left a lot, not only does it turn the car left, but it will also seem to turn the road left, because often left turning the car occurred when the road was turned left. So there's a bit of causality thing which this model hasn't really understood and needs to be disentangled. Anyway, in order to stop the Java callback loop, you need to press the Alt button, which will essentially reduce the traffic inside the Colab notebook. So below that gameplay piece, I've also got some kind of debugging things where I was looking at what do the actions mean in another of the games. Here is Pong. I've had a play with some of the other games as well, though I agree with the author that pole position has some of the cleanest output. Depending on where you start, the Pico Doom can also be quite impressive, though it's very prone to essentially moving out of distribution because this was only trained on a limited amount of the Doom dataset. Anyway, I really encourage people to have a look at this TinyWorlds because it is inspirational, even though the quality of the images or gameplay is pretty limited at the moment, because this whole thing has been put together very nicely with a lot of clear thinking about how this whole thing should be put together. Okay, to wrap up, I've covered some ideas here about how modern image models are trained, which has included some speculation about how some of these proprietary models are being trained. But throughout this, there's also been a thread about annotating data and how this can be used to actually get the model to go forwards from annotations back into real world or world model use cases. And we finished up with a concrete hands-on about how to do this at smaller scale. Hopefully this will inspire you to download the Colab, have a go at running it, so you can get your hands-on with frontier kind of thinking, even on a small scale. Thank you for watching the video. Please comment if you liked it, or if you have other ideas about videos I could make. I particularly enjoy making videos which are at the frontier in terms of thinking, but have concrete examples of things you can do. So here I've got a Colab which at a small scale explored the idea of world models, but there's also been a thread of how world models are constructed running through image models all the way to the very latest stuff. Looking forward to next time. Cheers.